Okay, yeah, please, Yuri, go ahead.
Yeah, hello everyone, thanks for coming. So maybe I'll briefly review where we stopped last time, and I'll start with discussion of solitons. So general scalar solitons are solutions to this system of equations. So these are general scalar manifolds, which we think of as Riemannian metric G and two integrable complex structures satisfying the usual generalized scalar compatibility assumptions. So from this you can cook up Ricci curvature, and you can cook up torsion free form. So H here is dci omega I, or what is the same is negative dcj omega j. So it's a free form, it's a closed free form. And you have this system of equations. So these equations, they appear independently in other contexts, not only in generalized scalar world. They appear in generalized Ricci flow, in pluriclosed complex geometry, but we will be considering in generalized scalar setting. And large part of the last talk was to show that this system of equation can be actually formulated in perhaps more direct geometric, I mean, this system has different geometric interpretation under certain assumptions on the manifold. So we assume that the structure is log non-degenerate. So assumption from now on that this is log non-degenerate. So which means maybe I'll just fit in here. Which means that if this is your manifold M, then on this manifold you have two proper analytic subsets. One where I plus j degenerates, and another where I minus j degenerates. And so these are analytic subsets, so their complement is open and dense. So, and on this open dense complement, you actually have invertible Poisson tensor, so you can define holomorphic symplectic form, and also you have this symplectic forms F plus and F minus. That was our assumption. So under these assumptions, we proved the following. We proved that you can necessarily construct, again, maybe let me scroll down a bit. You can necessarily construct two vector fields xi and xj like this on any soliton, and these vector fields, they will satisfy these properties. They will preserve Poisson tensor. They will be simultaneously I and j holomorphic and killing. So they actually preserve the entire structure. And perhaps more importantly, they will be xi plus xj and xi minus xj will be Hamiltonian with respect to the underlying symplectic forms. And this allows us to give characterization of solitons different from the initial equation. And this characterization is what we finished with last time. So let me go over it once again. So you start with the general scalar manifold, which is log non-degenerate. And you also you prescribe two vector fields, xi and xj. So this is part of your data. And you assume that this vector fields satisfy what corresponding vector fields satisfy on the soliton. So they preserve the entire structure, and xi plus xj and xi minus xj are Hamiltonian with respect to some underlying symplectic forms. But that Hamiltonian potentials, I call them psi plus and psi minus. And I also assume that this volume form, which is initially defined only where f plus is defined, and f plus is defined only when I plus j is invertible. So it's defined only on open proper subset of your manifold. So I assume that this volume form actually extends to a smooth volume form on the entire manifold. And we saw that this is necessarily true on a soliton. So you have these two volume forms. Then with these two volume forms, the Soliton equation actually is equivalent to the identity, to the equality between two volume forms, one which is defined by f plus and another which is defined by f minus, weighted by the corresponding potential functions. And you can explicitly write what the Soliton function is. So Soliton function is given by this. So that's the characterization of Solitons. And morally, I mentioned it last time, one can think about this as some sort of one-Ampere equation. In Scalar geometry, one-Ampere equations, they are characterized by certain identities on the volume forms of Scalar manifolds. So our goal for today is to set up relational interpretation. So I would like to consider a generalized scalar class. I recall what it is, and I would like to look for the solutions to this equation in a given generalized scalar class. And to this end, I will define some functional whose critical points will be exactly solutions to this equation. So let's start this part. So again, starting data as above will be two vector fields. So let xi, xj be vector fields on a generalized scalar manifold G, I, G, such that they preserve I, J, and G. So they holomorphic and killing, holomorphic with respect to both structures. So xi plus minus xj, this f plus minus Hamiltonian. And E, so with potentials psi plus or minus, and the corresponding volume forms extend to smooth global forms. Global forms. I don't assume that it's a soliton. I just take this data. So what I'm going to look for, I'm going to look for a soliton with this data in a given generalized scalar class. But I have actually to modify a little bit my definition of generalized scalar class because of the presence of these two vector fields. So what I'm going to consider is actually equivariant generalized scalar class. Equivariant generalized scalar class. So I consider group G. So this will be subgroup in the automorphism of Gij. So this is group generated by the flow of xi and xj. And yeah, actually, our assumption here, let's also add the commute. Again, this is always true on the solitons. So if we're looking for solitons, we need commuting vector fields. So I consider a group generated by these two vector fields. Well, they commute, and G is a subgroup of isometric groups. So these two vector fields, they actually generate a torus. They generate torus. Again, maybe I should add this, that here my assumption that M is compact. So, and I will consider the space of functions which are invariant with respect to this torus. So not all smooth functions, but only invariant on the direction of this torus. Space of G invariant smooth functions. Modulo constants. So now, as before, I can use this to infinitesimally modify my generalized scalar structure as in the flow construction. I take this space and I feed it into the Hamiltonian flow construction. So yielding deformations of the initial structure GIG. So I will not give you the specific formulas I gave them last time. I just recall that in this construction, one of the complex structures is fixed, another flows by Hamiltonian diffeomorphism, and since it's Hamiltonian, so maybe I should add that it's sigma Hamiltonian, that your Poisson tensor sigma also stays put. So we call sigma in this formulation is 1/2 commutator of I and J, G inverse. So you can start with a given structure, and you can apply all possible Hamiltonian flow constructions which are generated by one parameter families inside this space of smooth functions. And the orbit of this flow construction is what we will be calling equivariant generalized scalar class. So the orbit of this construction in the space of all generalized scalar structures on M is G equivariant generalized scalar class, which we will be denoting script M G. So I have to introduce this class because I have to take into account the presence of this extra data. And I want this extra data to be preserved under the flow construction. And this is indeed the case. So what we can say in this situation. Maybe I'll just formulate it as a lemma. So xi and xj remain killing and ij holomorphic for any structure in the script mg. So whenever you change your structure, generalized scalar structure within equivariant generalized scalar class, this property of xi and xj being healing and j holomorphic, it doesn't change. Okay. So that's the first assumption which we had here. that they preserve, and I, J, and G, and they commute with each other. So this doesn't change. Now, what about this condition? What about being Hamiltonian with some potentials? Is this preserved? And what about this condition about these forms to be globally defined smooth forms? Well, they happen also to remain true under the flow construction. And maybe I'll just formulate this separate statement. Under the flow construction, again, maybe I want to be more specific, under the sigma Hamiltonian flow construction, generated infinitesimally by phi in the space of G invariant smooth functions, modular constants. We have the following variations formula for the Hamiltonian potential psi and for this global volume forms. So variation of psi, say plus, will be negative. So, and the right-hand side is a global defined smooth function on your manifold. And the corresponding variation of the volume form would be, maybe again for plus, and for minus it's analogous. So that's a statement. So it's a matter of calculation, direct computation. Maybe I'll just mention a couple things here. That this global defined smooth form is being modified by an exact form. In particular, the total volume with respect, the total volume of this form doesn't change. And perhaps, and before mentioning this, I should of course underline that even though this is not immediately defined, it's not immediately obvious that this thing is defined globally. It is defined globally under the assumption that this thing was defined globally, right? Because remember, F plus only is defined where I plus J is invertible, and likewise is psi plus, but the volume form e to psi plus F plus and is globally defined. Which implies that this quantity is also globally defined. Okay.
Sorry, I have a question.
Yes.
Like in this previous lemma, I guess the claim is also that like as J changes, XJ retains its like relationship to the, I mean, sort of Xi and XJ are somehow fixed completely, right?
Yeah, they're just fixed and they're not defined through Lie form, right? So these are just fixed holomorphic vector fields.
Right. Well, and but there is, isn't there sort of a defining equation at the start for XJ, like coming from?
So if you have a soliton, you can.
Yeah.
Yeah. So if I see it. You can maybe I didn't formulate well. So if you have a soliton, you have specific choice of Xi and Xj, right? So in a soliton, you can choose Xi equals something like 1/2 I that I sharp minus grad F. Right.
But this is not that. It's just fixed.
Yeah, here, because we don't have a soliton, this will not necessarily be even holomorphic. It will be just a vector field.
Yeah, okay.
So we specifically take to start with holomorphic vector fields, so that maybe there, and our hope is maybe we can run Hamiltonian flow construction and modify the entire general scalar structure such that these vector fields will become exactly the vector fields defined by this Soliton
Yeah. Okay.
condition.
Sorry. I understand. Thank you.
Yeah, I'm sorry. Yeah, I sort of jumping between these two interpretations of xi and xj. So xi and xj are given by that formula only if we're sitting on the soliton. In general, we just take some holomorphic vector fields.
Can I ask a question?
Yes, of course.
So you said last time for a soliton, the Poisson structure is a constant times xi wedge xj.
In dimension 2, yes.
And in this construction, neither the Poisson structure or those vector fields vary. So doesn't that kind of immediately give you like a huge abstraction?
It does give some abstractions here. That is true. I will discuss it. I will discuss later. But yeah, that's in dimension 2. This observation. That's not in general.
Is there something in general?
I don't know, honestly. So there is some. Yeah, I guess there is condition against something. What is true in general, I think, is that if you evaluate. Oh no, actually, hold on. Yeah, perhaps on the non-degenerate on the non-locus where sigma is invertible, perhaps this is constant. So I think this is the best you can hope for. Double check actually. But yeah, even this I'm not sure. So I think this is true, but I need to double check. But kind of this is my guess. What would be the analog in the higher dimension? In higher dimensions. Does answer your question somewhat?
Mm-hmm. Yeah, thanks.
So we have these variation formulas along the flow construction. So we see how volume forms change. And our goal now is to use this to define a functional on the covariant generalized Scalar class. So functional on script mg. So when we follow the path, which is the kind of the mainstream path in Scalar geometry. So whenever you want to define a useful functional in Scalar world, you really most often define it through its variation. So you define through its variation, and then you basically you introduce a one form in this space, and then you check that this one form is closed, so it can be integrated to a function. So instead of defining the functional, we will really define closed one form on this generalized Scalar class. And to this end, I recall you that the tangent space to the generalized Scalar class is just this space of invariant smooth functions. So we need to define a linear functional on this space. That's what we want to do. And we define this functional as follows. I just want to follow the notation from the paper. So we'll call it new. And to highlight that it actually depends on the choice of vector fields, I put subscripts xi and xj. So it's one form on this infinite dimensional manifold. So we should be able to fit in element of the tangent space, which we think of as smooth functions. So if we want to evaluate this one form on a smooth function, then we integrate over our manifold M, phi multiplied by the difference of two volume forms, one with respect to F plus, another with respect to F minus. So that's that's a one form. It's linear in phi. If M is compact, you can always calculate this, and it will be a number. It actually, we have some examples where you can compute this number, even though M is not compact. Basically, because this is not really Riemannian volume form. It's weighted also by some potential, and if its potential in this volume form decays fast enough, or even on non-compact manifold, you can make sense of this expression. But so far, let's think that this is for a compact manifold. So let's see. To upgrade this closed form to this one form to a functional, we need to check that it's closed, and this is sort of the key computation which you have to go through. I'll just leave it as a claim.
Sorry, just a small question. Is it clear that this is well defined on, I mean, is the integral defined up to constants or?
Right, yeah, that's a good point. So I choose, yeah, that's normalization questions. That my psi plus and psi minus, they're Hamiltonians of certain vector fields, and Hamiltonians are defined up to additive constant. And yeah, I sort of swept it under the rug, and that's perhaps not right. Let me make this normalization. So my normalization for potentials is that total integral of e psi plus f plus to the n over n factorial, or minus likewise, is the same as Riemannian volume.
Thanks.
So yeah, this assumption we have to make. Well, all we need that they equal to each other, of course. And the property of being equal to each other is preserved under the flow construction because you change your structure by an exact form. All right, so claim that this one form defined this way is actually closed on MG. And it's a little bit subtle calculation compared with Scalar geometry, because in Scalar geometry, your generalized Scalar class is sort of trivialized by C infinity space. So it's basically can identify it with an open set in C infinity. And essentially, if you have variations in two different directions generated by two different functions, then these variations commute with each other. Here, elements of this space, they do not commute with each other, and the commutator is given by the Poisson bracket. So you have to take that into account. So maybe I should make it a little bit more precise. So any smooth function on your manifold defines right invariant vector field on this general scalar class, and we can calculate the differential of this form evaluated on this right invariant vector fields. And right invariant vector fields do not commute with each other, unlike the Kähler situation. And that's something you have to pay attention to. And yeah, kind of following up Mario's question, with such normalization, if these two total volumes equal to each other, this one form is independent of adding a constant to function phi, as we want it to be. We want it to be an element in the space modular constants. So with this claim in place, we can integrate nu xi comma xj to a functional. And of course, we would like to have a functional on generalized scalar class, or equivalent generalized scalar class. Unfortunately, it doesn't work quite like this, because the generalized scalar class supposedly can have quite a complicated topology. It's not necessarily simply connected. And in general, we don't have good understanding about topology or geometry of the generalized scalar classes, because it's something, essentially, it's something like the group of Hamiltonian diffeomorphisms. And groups of Hamiltonian diffeomorphisms are pretty complicated. So they're not that well understood. So to integrate it to a functional, we actually a priori have to take to a priori integrate, we need to take universal cover. So maybe this functional descends to the general scalar class itself. I mean, I don't know, and I don't even have intuition for whether it's true or not. So maybe I'll just write it as a question. Maybe Vasti has intuition, I don't know. Maybe write it like this: is nu xi xj exact on mg itself and not on mg tilde? Again, it sounds like a question about groups of Hamiltonian diffeomorphisms. And here, situation is even a little bit worse, because it's not the group of Hamiltonian diffeomorphisms which are well studied in symplectic geometry. These are Hamiltonian diffeomorphisms generated by Poisson tensor. And so it's a slightly more general thing, and perhaps they could be more complicated.
In the dimension 2 case, there is kind of a simplification though, which is that well, at least away from one of the places where like F minus vanishes, the symplectic groupoid of the Poisson structure will just be a cotangent bundle, so you can identify those elements as certain sections of the cotangent bundle, although there would be, it still may be complicated to figure out.
I see. So your point that if we do not consider one of the degeneracy loci, then on its complement, we can actually.
Well, I'm just saying that because I only understand the symplectic type in this way.
Yeah. Okay. All right. So yeah. So what's the statement for the symplectic type?
Well, it's just that the Hamiltonian that Hamiltonian class that comes from those Lagrangian submanifolds inside of the groupoid, and when the Poisson structure is like a wedge product of two bivectors, then I think in that case the symplectic groupoid is just a cotangent bundle, but the structure maps are deformed in a weird way. So you could still represent the elements as sections like that.
So there will be essentially a linear structure on general scalar class this way, or
I don't know if I don't think it's necessarily linear.
Okay.
But do you think it's a contractible space, or?
I'm not sure. I would have to think about it more.
I do know though that in relatively simple symplectic manifolds, this Hamiltonian group could have a weird topology and definitively be not simply connected. So I don't really know if we can expect this to be solvable easily. And the question Yuri raised, I don't know the answer either, but it could be that this guy is exact without the whole group being simply connected. So.
Yeah. Well, it also, yeah, you're right that this Hamiltonian diffeomorphism group in general are complicated. But maybe since we're sort of not that far from hyperkähler situation, or even a hyperkähler situation, perhaps they are a priori simpler. But I don't think that anyone actually tried to study it. So what are restrictions on the Hamiltonian diffeomorphism groups if your underlying manifold is a hyperkähler or has some other structure? Okay. So let me write down corollary of the fact that there is such functional. So let's actually give it a name. So this functional in the paper, we'll call it J. Again, let's put xi, xj in subscripts. And of course, J also depends on the base point, because it depends, you can start integrating from any base point in a given general scalar class, but choice of a base point only changes this functional by adding an overall constant. And we sort of don't care for the actual value. Well, we really care about the variation of J. Corollary is that generalized scalar structure M in a given general scalar class is GK soliton with vector fields xi and xj. So again, these vector fields are prescribed initially to you. If and only if M is a critical point of this functional J, xi, xj. So that's what I would call a variational interpretation of the soliton equation. And by generalized scalar soliton, I mean gradient steady generalized scalar soliton. So now let's see why it's true. Well, it's true because this functional has a critical point if and only if its variation vanishes. And this quantity vanishes for any G-invariant smooth vector, function phi, if and only if this volume form actually vanishes. So in general, you need to test it against all smooth functions, but because this form is also G-invariant, it's enough to test it only against G-invariant functions. And vanishing of this volume form, as we have seen, is missing ingredients in the soliton equation. So we have already all points characterizing soliton except for having this vanishing. Okay. Any questions? So this functional has some nice convexity properties, and you can actually calculate its second variation. Of G. So if you consider one parameter family of potentials in this space, then second variation of this functional is so I mean specific formula is not that important, but let me write it anyway. Some part of it will be important. So there will be three terms. So this will be one term, and there will be two terms which are positive. Plus G squared against plus volume form, and analogous term for minus. Okay, so that's the second variation, and let's see what does it tell us, and what are the terms here. So we have two terms which are strictly positive unless phi is constant. And we have a term which could have sign in general, but which has this volume form inside of it. And this form of second variation, it actually has an important consequence: rigidity of solitons and generalized scalar class. Some theorem, rigidity. So assume that we have a one-parameter family of generalized scalar structures. So it's one parameter family, and we assume that they are log non-degenerate.
Why doesn't the first term vanish?
First term does not necessarily vanish. So if you just start with some scalar structure and you take arbitrary, again, this family is arbitrary variation, this of course can be negative.
Oh, we're not at a soliton.
Not necessarily, yeah. If you're not on a soliton, it might vanish. Yeah, and the point of the next theorem is actually, since on soliton it vanishes, then you have rigidity. So that's, you can sort of anticipated what I wanted to say. So if you have a one parameter family of log non-degenerate gradient steady solitons lying in the fixed class in MG. Okay, maybe let me be a bit more careful, where G is generated by these two vector fields xi, xj, and this time these are vector fields associated with the initial soliton M, G0, I0, J. So the conclusion is that then this variation is stationary. So you cannot have infinitesimal variations of the soliton in a fixed class. And yeah, prove essentially. So Francis already observed what's the key here. That for any GT, IT, J, J is let me try to write it as a bold J, so to distinguish from the complex structure. Any generalized scalar structure under this variation is critical for this functional J. So you actually have the second derivative vanishes. On the other hand, what the second variation is, so I'll just copy it here. So it has three terms, and since it's a soliton, this also vanishes. And these two are positive or non-negative. So the only way it could happen is that your Vt are constant. And since Vt is constant, your variation is also constant. So you really is not moving at all. So it's a little bit suboptimal result, but it's still helpful. Why is it suboptimal? Well, because there are some variations which we don't know whether they preserve the class or not, and we expect that your soliton will still be invariant under those. For instance, we expect, maybe I'll just write it as a question. So let K be maximal compact subgroup in the automorphism of MGI. So, and I can ask, is it true that K preserves, yeah, I shouldn't say maximal complex, it's already complex. So, is it true that K preserves J? So we don't have answer to that. Because one parameter variations generated by one parameter subgroups of these automorphism groups, we don't know whether they preserve general scalar class or not. So I have some time left. I was contemplating whether I should discuss existence and uniqueness on Hopf surfaces or not. Perhaps I will not go through the actual proofs. I'll just give you the main statements, and I'll explain where we use these functionals in the proof. So try not to take too much time. Any questions at this point?
And yeah, but sorry, I guess for the question, I guess like what the theorem ends up showing is that like automorphisms which also preserve sigma will preserve J, I guess. Is that the point?
Well, yes. Well, it's if they also preserve sigma, it's obvious it would preserve J in log undegenerate case.
Oh,
well, maybe not that obvious. Well, it's true in 4 dimensions. Yeah, actually, I'm not sure. Yeah, the only point which I want to make that this is still a little bit unsatisfactory because assumption of staying in one general scalar class is strong, and we don't at the moment have nice tools to verify it because we don't have good understanding of general scalar class still.
Right.
So that's perhaps really the drawback of this rigidity result. And in general, this functional and the generalized Ricci flow, the hope is that it will allow us to get a better understanding of these general scalar classes. So now I want to discuss some specific setting of generalized scalar structures in complex dimension 2, and in the end there will be one point where we'll need to apply this these functionals and this rigidity result. So overall, I will call it existence and uniqueness of generalized scalar structures on Hopf surfaces. And I need to start with sort of taxonomy of
Sorry, Yuri.
yes.
Yes. One comment about your second variation. So when you calculate the second variation, the first term shouldn't have a second derivative of pt with respect to t instead of first. I'm a bit confused.
Yeah, because in first variation of J, you don't have derivative at all, right? So this is first variation of J essentially.
Yeah, but phi is a tangent element, right?
Yes.
So when I take if I take in derivative along a path, I don't get the phi dot.
You get phi dot, yes. So this is phi dot. Yeah, phi sub t, it's not derivative. It's just notation. Maybe I should remove t from here.
But I think like in the way the one form nu is evaluated above, it would be more like d phi dt. Like here phi is a path, up there phi is like a tangent vector, I think, right?
It's a one parameter family of tangent vectors, tangent vector fields.
Yeah, but I guess like above where you apply nu to phi, that like if you compute the first derivative of J along a path, you'll get nu applied to d phi dt. Is the point?
Yeah.
if I'm not mistaken, right? Like that.
No, you will have nu applied to phi.
But then how could a second derivative show up? Yeah,
There is no second derivative, there is first derivative.
Oh, okay, sorry. Yeah, I understand.
So this whole thing is first derivative of this expression.
Okay, yeah, sorry. Yeah.
But still, you have a one parameter family of functions,
Yes.
which you interpret as elements in the generalized character. And then
yes.
If I take derivative, then the tangent at phi is phi dot t, right? The tangent at phi t is phi dot t.
Yes.
And therefore, in your formula for the second variation, it should appear a second derivative of it should be the derivative of the tangent vector.
No, you don't get second derivative. So you see this expression, this second derivative of j is the same thing as first derivative of this one form.
Yeah, my point is that if you evaluate this along a path of phi t's, then the tangent of phi t is the derivative with respect to t of phi t. So this is what should appear in this functional. Should be the integral over m of the derivative with respect to t of phi t.
Sorry, I'm not following. I probably am missing something simple what you're trying to say. So so maybe let me write it this way. So maybe let me put phi t here everywhere. So this is my family. So this is phi t. So I define j in this case. So j by definition is integral from 0 to t nu xi xj of phi t phi s ds. Does it make sense?
Yeah.
So second derivative of this bold j is the same as first derivative of nu of phi t.
Yeah, no, my point is that nu of phi t is the evaluation of nu at the tangent vector along the curve. And the tangent vector along the...
Okay, yes.
And the tangent vector along the curve is the derivative of phi t with respect to dt.
No, in this interpretation, phi s is already the tangent vector along the curve. You integrate this curve, and you yeah, perhaps I see where confusion kind of comes from. So phi s is already tangent vector along the curve.
Okay. My point is that things get better if you have a second derivative there instead of a first derivative, because it means that along straight paths, the first term vanishes and you get something positive. But maybe this is not the case.
Well, it vanishes along constant in time phase, which is exactly consistent, which exactly represent a straight path.
Okay, so your phi t is actually the tangent vector, and then if I have a straight path, then this first term.
Yes, precisely. Okay. Yeah. Sorry for the confusion. Okay. Yeah, that's what it is. And yeah, so this was observed actually by, maybe I should mention it. I didn't mention it today. That this functional in non-degenerate case where both I plus j and I minus j are invertible was discovered by Jeff and Vesti in their joint paper. And that's basically just an upgrade of their functional to the situation where I plus j and I minus j are allowed to have degeneracy on proper analytic subsets. I mean, even though it looks like not a big difference to what they done, guessing what this functional should be and checking all the necessary parts, it wasn't trivial. And actually, the way we arrived at this functional is interesting on its own. But yeah, perhaps don't really have much time to talk about it. So you cannot really guess this functional. So guessing it's I'm not sure how to do it. So we got the intuition from specific examples which we had in hand. Anyway, so before I move on, any questions?
But then don't you get just uniqueness on the of this log non-degenerate gradient steady solitons on any?
Yeah, so that's a problem. You don't have uniqueness in general, because if you integrate only along straight path, you will not cover the entire generalized scalar class. It is a funny, unexpected thing about Hamiltonian diffeomorphism groups, which I wasn't aware before I started doing this. That exponential map for group of Hamiltonian diffeomorphisms, and again, essentially you can think of MJ as a group of Hamiltonian diffeomorphisms. It is its orbit anyway. That an exponential map is not surjective.
Right.
And since it's not surjective, you actually have to allow for time-dependent.
Okay, so when you define the generalized scalar class, you are actually allowing one parameter family of functions which vary with time.
Yeah, and you sort of have to allow. It's
Okay.
it doesn't make sense to consider only time-independent ones. Yeah.
Well, there is a result by Banyaga which says that this whole group is generated by time-independent Hamiltonians, but that doesn't help necessarily.
Yeah, you basically can split your time-independent path into several segments. Each of them is time-independent.
Yes, something of that sort. Yes, a finite number of them. Yes.
Well, actually, now thinking about it, it might be helpful here, right? Because this term vanishes for each of the segments.
Another remark is that this time-independent Hamiltonian diffeomorphisms, they play the role of geodesics in this infinite approach we developed with Jeff. So it's a natural question of geodesic connectedness. I always thought there is no chance to get one, but who knows? Perhaps there is a partial geodesic connectedness or something.
Mm-hmm. Yeah, and you also showed convexity along the generalized scalar Ricci flow, right? You have
Yes.
a separate calculation. Yeah, we didn't include it here, but yeah, perhaps it also holds. More questions or comments? So yeah, Hopf surfaces. Yeah, I'm not sure. It's a bit unrelated. Jeff, what do you think? Should we discuss Hopf surfaces? Maybe we can call it a day. It's been an hour already, and we intend to make it so short.
It's I mean, I suppose it's up to you. I mean, if you just want to state the results, 10 minutes or something, or maybe even
yeah, all right. Yeah, maybe
I don't know.
This. Okay. So all right, so let me maybe recall your taxonomy of the Hopf surfaces, because there are different people call Hopf surfaces different things, and even the same person, different papers call in different Hopf surfaces. They mean different things. So yeah. So let me maybe set some notation. So first we define primary Hopf. So primary Hopf surface is a quotient of C2 minus the origin by a contraction. So A is a holomorphic map from C2 minus the origin to C2 minus the origin, which is holomorphic contraction. So holomorphic contraction means if you apply it many times, you will push everything, any compact subset here, into a neighborhood of 0 here. So actually, since it's a holomorphic map by Hartog's theorem, it extends across 0. So and by Kodaira, in appropriate coordinates on C2 minus the origin, this contraction can be made either just multiplication by diagonal matrix. So alpha, beta are two complex numbers with norms between 0 and 1. And another option is a little bit more subtle. It's sort of like a Jordan block. So it sends Z1, Z2 to beta to the Q, Z1 plus lambda Z2 to the Q plus beta Z2. So here norm of beta less than 1. And lambda just any complex number. So it sort of mixes coordinates Z1 and Z2 here in a polynomial way. So these are primary Hopf surfaces. And then secondary is just.
Where does the comma go in the?
Sorry, what's the question?
It like this second line A just looks like it's valued in C.
Where here?
Like where does the comma go? There's no in your expression for A.
Oh yeah, sorry. I see your. So yeah, it's a comma. Yeah, sorry about that.
And that's a 9, beta to the 9.
It's Q. It's just some power.
Oh,
The Q is an integer, positive integer power. Okay. So yeah, you should think of Jordan block here in this second case. For instance, if Q equals 1, it's literally this Jordan block matrix. And secondary are free finite by holomorphic quotients of primary. So this is sort of abstract definition, but these are actually understood. So Kato actually described all specific groups which appear in here for these surfaces. So these are Hopf surfaces. Primary Hopf surfaces, they all are diffeomorphic to S1 cross S3. And Kadaira proved that any complex structure on S1 cross S3 is actually the one coming from the primary Hopf surface. So these are understood. And the question which I would like to answer is existence and uniqueness of generalized scalar structures and solitons on Hopf surfaces. Well, clearly there is no uniqueness of just general scalar structures because you can deform those. But the uniqueness of solitons makes sense in the appropriate formulation. So you really have two types of generalized scalar structure. There are two sorts of in dimension 4. So since we have real dimension is 4, we have odd and even generalized scalar structures. And analysis of those two is sort of completely different all the way up to the very end, where in the end you get almost the same classification answer. So, which is kind of amazing. It suggests perhaps there is a unified approach to the two, but I don't know. So in odd case, what you have is that I and J commute. This is feature of dimension 4. And in the even case, this is actually, in this case, in the case of Hopf surfaces, it's equivalent to being log non-degenerate. Right, so you have these two sort of opposite to each other situations. So here your sigma is 0, your Poisson tensor. Here your Poisson tensor is invertible generically. So this situation, at least existence of generalized scalar structures, was studied by Marco and Vesti. Theorem. So what they proved is that odd generalized scalar structures exist only on diagonal primary Hopf surfaces and their cyclic quotients, I mean specific cyclic quotients. Their cyclic secondary specific. So this case of this Jordan blocks is forbidden, and not all 3 finite Holomorphic quotients are allowed either. But there is a complete answer to both of these questions. So that what concerns the existence part in the odd case. And in our joint paper,
sorry,
yeah.
Just to be sure I understand. So the theorem by Vesti and Marco is that if I consider generalized scalar structures of odd type on a secondary surface, that this has to be diagonal primary Hopf.
So if it's secondary, it has to be a cyclic quotient of the diagonal Hopf.
Okay.
And if it's primary, it has to be diagonal Hopf.
Okay.
And those do admit odd generalized scalar structure.
Thanks.
Mm-hmm. And in our paper with Vesti, with Jeff, we proved that these admit. Okay, maybe that's not exactly what we proved. Maybe right. Let me write specifically what we will prove, that diagonal Hopf surface, diagonal Hopf surfaces, surface, maybe I call it MI, admits a unique odd generalized scalar soliton up to automorphism of M and I, scaling of geometric G. So let me call this soliton M, I, G, J, G. And up to go swapping J and negative J. And this is something I discussed, I think, in our last series of the learning seminars. And essentially, the proof consisted of 2 parts. You first prove uniqueness in a generalized scalar class, which is basically maximum principle. And this maximal principle is possible because in this case, general scalar class has linear structure. So in this case, sigma is 0, Poisson tensor is 0. So really your Hamiltonian diffeomorphism group is not a Hamiltonian diffeomorphism group, is something simpler. It has a linear structure like in the Keller case, and it allows you to apply maximum principle. And then basically you study carefully the general scalar classes, and this is some cohomological question. Cohomological computation. So that essentially almost completes this case of odd structures. So to complete the case of odd structures, you also need to address secondary quotients. So we didn't do it in our paper. So to clean things up, we added this statement in the paper, which I'm now discussing, the one with Vest and Jeff. So that's about odd structures. So what about even structures? So even GK structures. So it turns out that the answer is in the end of the day the same. So theorem so even GK structures.
Can you say again, what do you mean by this cohomological computation? What is?
So you can define in the odd case, in the commuting case. In the commuting case, you can define certain homology group associated to any general scalar structures. And but basically what this gives you is uniqueness in a general scalar class, where this class is actually a class of this homology group. And then you need to understand what are possible cohomology classes in this group on a Hopf surface, up to the action, up to scaling, and up to the action of automorphism group. And what we did, we proved that this class, basically there is only one element up to this equivalences. So I can probably write explicitly what this class is. Give me a second. So, so it's something like del bar closed forms modular certain operator on functions, and this operator on functions is defined using the splitting in your tangent bundle. But in the computing case, your tangent bundle splits into two holomorphic sum bundles. One is where I equals j, and another where I equals negative j. And you can cook up this mixed Laplace operator, not Laplace, sorry, mixed complex hashing. So this is the cohomology space with which I'm talking about. Does it make sense? So basically, so this is finite dimensional space, and you can explicitly calculate what it is on a Hopf surface using some basic knowledge about complex geometry of a Hopf surface. Mario, does that answer your question?
Yeah, thanks.
Mm-hmm. And what we proved in our paper with Vest and Jeff is basically the same statement as before. So this even structures, they exist only on diagonal primary Hopf surfaces and on their cyclic secondary quotients. So that's about existence of even structures. Now, what about uniqueness of solitons? Uniqueness of solitons. So existence was actually resolved in our paper with Jeff. So we had explicit construction of pluriclosed solitons. So essentially, we didn't care about second complex structure. And what we showed that you can actually pick second complex structure to make it either even or odd. So both existence of even and odd solitons actually is something following from our paper with Jeff. And really, the only remaining part was the uniqueness of solitons and Hopf surfaces. So what we had regarding uniqueness, again, in our paper with Jeff, is that we had uniqueness under assumption of symmetry, S1 cubed symmetry. This is a maximal torus in automorphism group of I. So if you assume that your metric is invariant under this maximal torus, then you can prove uniqueness. So therefore, now the question is why, if we have an even generalized scalar soliton on a Hopf surface, why is it invariant under this maximal torus? Question. Why GK soliton, even GK soliton on a diagonal? So let's consider diagonal case first. This is the essential one of surface is necessarily invariant under a maximal torus. And we have already a partial answer to this question. We know it is true because we know what is true. We know that there are already two vector fields, xi and xj, under which the structure is invariant. So already have xi and xj generating at least S1, 2. So you know that if you have soliton, a priori you have two-dimensional symmetry. So what the question which is remains to be answered, why there is a third vector field. And yeah, perhaps I will not go into details really, but the point is that rigidity result, which I mentioned above, rigidity result in a given generalized scalar class implies existence of a third vector field. And next, once this existence of third vector field preserving the entire structure is established, you get three-dimensional symmetry, and you can invoke our result with Jeff. So the final statement is as follows. So maybe let me state it precisely. Theorem. So let's M, G, I, J be an even gradient steady soliton on a Hopf surface. then its primary cover. By primary cover, I mean, so this might be secondary, might be primary. If it's secondary, you take its cover, so it's a primary Hopf surface, so it's maybe a trivial. Is isomorphic to the generalized scalar soliton constructed in strings up to, so what is automorphism? What is allowed? So we allowed to act by automorphism of mi. We are allowed to scale metric G, and we're allowed to swap J and negative J. So that's a uniqueness statement. So bottom line is that the set of Hopf surfaces which admit generalized scalar structure either odd or even is the same for both. And all those which admit even or odd generalized scalar structure, they admit unique generalized scalar soliton. Okay, so perhaps I'll stop here. Thanks for attention, and yeah, I'm happy to answer any questions.
Yeah, thanks, Yuri. Are there any more questions?
What is you were going to say more restrictions about that Poisson structure?
Oh, right. Yeah, I didn't mention that. So what we proved is that, so you have, if you consider, say, diagonal Hopf surface, C2 minus the origin, modular contraction by this alpha 0, 0 beta. This is diagonal Hopf. Let me call it M and I. So it has a canonical holomorphic Poisson tensor Z1, Z2, del Z1, wedge del Z2, where Z1 and Z2 are coordinates in C2. So this is Poisson tensor, let me call it pi. It's a complex Poisson tensor. And you might ask, so what generalized scalar structures? So let me ask it this way. Let me write the statement. So if okay, sorry, I'm trying to think what is a clear way to say it. Question. So can we extend M, I, and multiple of pi? So maybe this multiple will be W times pi. So W is a complex number. To an even GK structure MIJG such that the real part of omega pi is precisely sigma, that is 1/2 IJ G inverse. All right. So we know that any even GK structure in dimension 4 has a generic and non-degenerate Poisson tensor holomorphic with respect to I. So when it can be made exactly this W times P times the canonical Poisson tensor. And the answer is if and only if these constants, this multiple of this Poisson tensor is real and non-zero. So specifically, you cannot take multiple which is not purely real of this Poisson tensor and associate it to some generalized scalar structure. So the way we guessed that such statement should be true is exactly as you suggested, because we knew that it should be true for solitons, and we sort of believe that if you start with any structure, it has to converge to soliton in the limit, even though we don't have this statement in general, only in some special cases, we expect it to be true. And based on this expectation, we understood that there should be restriction on Poisson tensor, which can be attached to a generalized scalar structure on a Hopf surface. And so we basically, after you guess what should be true, it's then easier to prove.
The Soliton condition was also a real multiple?
Yes, in Soliton condition, we knew, because you had these two vector fields, which are real vector fields, and you knew that this has to be, so that this has to be a real multiple of that. Yeah, it's a real tensor and has to be a real multiple of that one.
Why is it true? How do you show that it's true? Is it difficult?
I wouldn't say it's difficult. I do not particularly like our argument the way we see it. It's a little bit ad hoc. Well, basically, the way we show it, that in general you can prove that sigma allows to recover the restriction of Lie vector fields, and in dimension 4 they opposite to each other, not entirely of course, but restricted. So I and sigma, maybe I should say this, I and sigma alone, without any knowledge about the metric, allowed to recover restriction of those on the canonical divider, which is the union of two elliptic curve inside your Hopf surface. You have this E1 union E2. So this is set where Z1 is 0, and this is set where Z2 is 0. And again, by analyzing automorphism of Hopf surface, you can assume that this is the same as the locus where your Poisson tensor vanishes. So if you a priori take any generalized scalar structure on Hopf surface by applying automorphism of Mi, you can assume that your okay, we actually already assumed that the Poisson tensor is multiple of this one. So its zero locus is where the Z1 vanishes and where Z2 vanishes. So E1 is an elliptic curve and E2 is elliptic curve. And you can recover this vector field restricted on this elliptic curve without knowing the metric. And you can apply the same logic to J and sigma. They also should allow you to recover those. And basically, it gives you some compatibility between these two. Between these two ways of recover the two vector fields, you have compatibility which forces sigma to be real multiple of this Poisson tensor. Yeah, sorry, it wasn't very helpful, but yeah, again, I don't particularly like our argument, so maybe perhaps there is a better one.
What are the other examples of solitons? Is there hyperkähler example?
Well, hyperkähler, well, they are all solitons trivially, where you can just take soliton function to be 0. You can take f soliton vector function 0, and actually vector fields also will be 0 because your Lie form is also 0. You don't have any torsion. So they are solitons, obviously, and we expect that there are no solitons on hyperkähler backgrounds other than those. Yeah.
But those ones don't satisfy that condition.
Which condition? Sorry.
Well, that the Poisson structure is a multiple of
Well, it is a multiple. Oh, no. Well, yeah, again, as I said here, perhaps the correct formulation that it's not a multiple, but rather that if you evaluate sigma on xi wedge xj, you have a constant. This is the true statement. And if xi and xj are linearly independent, it forces sigma to be a multiple.
What does it mean applying sigma to?
Well, sigma, oh, sorry, sigma inverse, yeah.
But also, I mean, the question, and or at least like the answer is only for Hopf surfaces. So I mean, so yeah, these hyperkähler metrics.
Yeah, the question and the answer, this both are for Hopf surfaces. Yeah, that's true. But I guess, yeah, Francis is interested in this interpretation that Poisson tensor on a soliton and somehow often dictated by the soliton vector fields.
I think it's definitely like it's a sort of non-Kähler phenomena. I mean, like I think hyperkähler metrics you can interpret as GK, I believe, with sort of, well, I think basically any Poisson tensor on these, on like a hyperkähler four manifold can be realized as a Poisson tensor associated to a soliton, which is actually just hyperkähler.
Yeah.
If I'm not mistaken, I think you could probably get any complex multiple at like any holomorphic 2-0 form.
Oh.
So yeah, so far we have a very small set of examples where we can meaningfully apply this observation about Poisson tensor. And yeah, probably this set of examples is not really much larger because it's only specific to dimension 2, complex dimension 2, and complex dimension 2 is sort of getting closer and closer to understanding what is the exhaustive list of solitons.
Well, we do have, I mean, for dimension 2, it is complete, right? I mean, we now know these are the.
Oh, for compact, yes.
Compact.
This is, well, yeah, okay, for complete.
Sorry, yeah.
It's not as clear.
I guess I was just wondering because the fact that the Poisson structure is so simple, I guess it tells you that the symplectic leaves have to be pretty. They can't have. I think that implies that they can't really have higher homotopy groups and stuff like that. I was just wondering if something like that would hold in higher dimensions as well.
Mm-hmm.
But I guess in that case, the hyperkähler one, then that's not true, I think. Like a K3 surface would have higher homotopy groups.
Yes. Well, no, actually, I don't know what are the symplectic leaves for K3 surface.
Well, if you just take the holomorphic symplectic form, so it's the entire. It's the entire K3 surface.
It's the entire K3 surface. Okay, yeah. Yeah, I understand what you're saying.
But like for all of these other ones, the symplectic leaves, the universal cover will be contractible, I think.
Yes, that's true here. Yeah, perhaps it's a phenomenon related to the dimension and to the fact that these two vector fields in compact setting are non-zero and not proportional to each other. So I think this is really the key to this fact. Basically, they generate torus, and you can then complexify their action, and you get the action of C star squared. So you get like an open dense orbit, and that's exactly where your Poisson tensor is non-degenerate. That will happen on a Hopf surface, and probably, I mean, there is no other options in general. If you have two independent vector fields.
Mm-hmm.
I have a question.
Mhm.
If you put together your results and the one by Este and Marco about the existence of general scalar structures,
Yes.
you just say that a general scalar structure exists only on diagonal primary half or their cyclic secondary quotient, right? So there is this paper by, I think it's Drabowski, on moduli spaces of Hopf surfaces, where he shows that essentially to have a Hausdorff moduli space of complex structure on the Hopf surface, you need to rule out the non-diagonal ones. So, I mean, this is a bit kind of, I don't know, it's like a bit surprising to me because so typically you find these Hausdorff moduli spaces when you impose some canonical geometry and so on. But here it seems that the general scalar condition itself is a GAT condition. It's like it's able, general scalar is already able to rule out this this non-separable phenomenon. I don't know if it is a manifestation of the fact that any general scalar structure actually admits one of these solitons, and this is just something very special from Hopf surfaces, or there is something more.
Yeah, that's something we discussed with Jeff for some time. It should be related one way and the other to some stability questions, because having this non-Hausdorff points, which you have to remove, are exactly some manifestation of non-stability of these complex structures. And non-stability of complex structures is already known to be something related to the long-time convergence of geometric flows, of Ricci flow, Keller-Ricci flow. So the fact that these are non-stable, perhaps exactly a manifestation of the fact that they do not admit solitons.
Okay, so you, in more general manifolds, what you would expect is something is more related to the soliton equation rather than the general scalar condition.
Yeah, and actually, we believe we discussed it with Jeff several times. Probably it's even related just to pluriclosed condition alone, and not specific to generalized scalar, and it will be much more interesting. And again, this is perhaps where your results about this holomorphic current algebroid and stability might play a role.
Yeah, probably in higher dimensions, the phenomena sort of separate, and I would imagine there are probably GK that don't admit solitons, maybe.
Yeah, that's probably true, but again, there should be at least implication in one direction.
Yeah.
So yeah, it's sort of it's not a complete coincidence. That's what I wanted to say. There is probably something to it.
Just probably there are some, but just curious, is there any well-known example of general scalar manifold which does not admit a soliton?
Well, yeah, that's the one also we're working for some time. This Inouye surface. There is parabolic Inouye surface. That means general scalar structure is actually the one constructed in the paper by Lebrun. And it doesn't admit soliton for simple cohomological reasons.
Okay.
Basically, if you run the flow, the volume of one of the divisors blows up. But what happens in the limit exactly, that we do not understand yet.
Yeah, yeah, like he said, those also don't have C10. It would be nice to have an example, like an odd type. Sorry, like a log non-degenerate GK structure in higher dimensions where first term class is 0.
Right.
Which does not admit a soliton.
Mm-hmm.
Well, okay, yeah, I don't know. Thanks, Yuri.
Yeah, thank you.
And